Okay, 3 atoms with atomic radii of 2.0, 3.0, and 4.5 are arranged as shown in the figure. Find the distance between the centers of atoms A and C. So here's an interesting application of where solving a triangle is useful. So we know bond lengths of atoms, which in general you just think about as, you combine the radii. So here this bond length would be 2 plus 3. So this distance here is 5, and then this distance here, 3 plus 4.5, is 7.5. But maybe we want to figure out what this distance is. Okay, now somehow they were able to get this angle here, but from there, do we have enough information now to solve this triangle so we can get this length? Right? So there's so many applications in engineering, chemistry, biology, where solving triangles is very useful, not just in surveying. But, we learn how to solve right triangles in chapter 2, but obviously in real life, you want to be able to solve any kind of triangle. And that's what the law of sines and cosines allows you to do. You can solve any triangle. So, okay, but up to this point, we haven't learned the law of cosines, so we can't use the law of cosines. And we see we've got two sides, and if we had an angle included between those two sides, then we could use the law of cosines, but we haven't learned that yet. But even in this case, we have an angle that's not included between those two sides. Now, we know that this falls under the ambiguous case of the law of sines, which we're going to actually more officially learn about in the next section. And I'm not sure why the textbook is giving us a problem like this here, because really this opening section we learned the non-ambiguous case of the law of sines, where you've got two angles and a side length. But I think the reason why they're giving us this is because there is, when it comes to the ambiguous case of the law of sines, it can end up being the case that it's kind of not ambiguous, in that even though we do have two sides and a non-included angle, this triangle still could be fully constrained to where there's only one answer here. So I think that's why they're giving us these problems. That's what it's going to turn out to be in this case, where this triangle happens to be fully constrained. So, but we'll talk more about the ambiguous case in the next section. But okay, so if we were going to use the law of sines here, we could do it because we've got, so okay, like we don't have two angles, so we can't just automatically get a third angle like we could with the angle side or angle side angle case. But we still, if we want to set up the law of sines, we can say, so sine of 18 degrees over, and then we've got the side length opposite of that is 5. All right. Now we can do the sine of angle C. Okay. And then opposite of that is side length 7.5. All right. So one equation and one unknown. Beautiful. So we solve, let's solve for C, angle C. So we've got, let's see, it's 5 times sine of C is equal to 7.5 times sine of 18 degrees. So sine of C over, okay, so let's see. We've got 7.5 times sine of 18 over 5. Okay, so now, but this is just a number, right? So what we need to do is take the inverse sine of both sides of this equation. That takes out the angle C, and we've got okay, so we can just put this straight into inverse sine with all of the decimal points, and there we go. Now, but the issue comes in that, well, as we know from solving trig equations, we introduced this inverse sine into the equation to solve the equation. So we have to think about the big picture of the inverse trig function. It's just like if we had x squared is equal to 16. Solving this equation, well, we take the principal, the root of both sides, but we have to, in this case, we have to put plus or minus. Even though the principal root of 16, just as it sits, is just 4. When we're using a principal or an even root, an even principal root in an equation, we have to think about the big picture, the plus or minus here. So this is plus or minus 4. It's same thing with inverse trig functions. Even though like inverse sine of 0, just as it sits, is just 0. If we used inverse sine to solve an equation, then we would have to think about, okay, well, there's two angles. Well, actually, there's an infinite number of angles that when you take their sine, you get 0. But like if we're thinking about between 0 and 360, 0 and 180 degrees, the sine of 0 degrees and the sine of 180 degrees is equal to 0. We have to think about that, right? When it comes to solving an equation using an inverse trig function. So now here, when we were solving trig equations and there was no problem we were dealing with, we just listed out there was an infinite number of angles, right? With the inverse sine of 0, there's an infinite number of angles that when you take their sine, you get 0. Because it's 0, it's pi, and then it's any angle that's coterminal with those angles. So it's an infinite number of angles. But we don't need to consider that here, those infinite angles, because we know we're dealing with an angle of a triangle. So it's not going to be a negative angle, and it's not going to be an angle greater than 360. So all we need to think about when it comes to solving triangles in this case is there's going to be two angles to think about. In most cases, sometimes actually you only get like with like inverse sine of 1, there's actually only one angle between 0 and 360 that satisfies that. But in most cases, there's two angles that come out of it. So here, for example, the sine is positive in the first and second quadrant. So the sine of this angle is going to equal this. But then if we find what angle in the second quadrant has this as a reference angle, so we take, okay, the sine of this angle is also going to be equal to this. So that's the two possibilities. Now, again, we're going to get more into specifics on the ambiguous case in the next section. But what you can do is, though, the way you can think about it is we could actually look at these angles, the setup here of the problem, and see, well, maybe one of those angles is not possible. So we're given 18 degrees. We know that's fixed. So what if we take this other angle and add 18 to it? Okay, well, actually, that's not greater than 180. There was another problem we worked in this section with gears where we got something greater than 180. And so that meant that it was impossible to have this as an angle. So I'm not sure why the textbook is giving us this problem, since we haven't studied the ambiguous case yet, because now there's two potential triangles. Well, okay, maybe we can look at the constraints of this and see that there's no way that angle C could be 152. I mean, visually we can see that it seems that though there's no way this could be 152 degrees. Because, okay, yeah, what we can see here is that, so this side of the triangle is going to 100% have to be the longest side of the triangle because of the way it's set up, because it's these, think about it, like these two atoms are directly next to each other. These two atoms are directly next to each other. So how could this possibly be shorter than this distance or this distance? I mean, even if it can't even be equal to this distance or this distance, which means that this is going to have to be the largest angle of the triangle. Like, we're going to talk about this more in the next section, but a way to analyze triangles is that the largest angle is the side length across from the largest angle of the triangle has to be the longest length side. Has to be. Because that's the idea. It's like it's the angle spread out. So it's that side spans the longest range. So, okay, in that case, if this angle C was 152 degrees, okay, and again, you add 18 to that, you get 170. So that would mean that angle B would be 9.6. There's no way this angle could be 9.6. Because even then, like you can see, that's less than this. So that means that this side length would be the shortest side length. That's not possible. So that is enough to say that we can eliminate this angle, and so angle C has to be this 27.6148. Okay, but we're not done because what we want is this distance from C to A. But now we can just use the law of sines in the non-ambiguous case because we've got two angles and a side length. We've got three angles now technically and two side lengths, so we can do whatever we want. Now it's easy. Once you like get one extra piece of information about the triangle, well then all of the congruence axioms and techniques open up, right? So okay, let's try and use given information. So let's use sine of 18 over 5 is equal to, so now we need to get angle B here because we need to solve for this side length. So, okay, this plus 18, and then 180 minus this is going to be angle B, 134.385. So, okay, sine of this is 18 degrees, 134.385 over, and then this side length B. That's what we're looking for. So, okay, if we cross multiply, we can see that B is going to be equal to 5 sine of 134.385 degrees over sine of 18 degrees. So B is going to be equal to, so let's see, sine of 134.385. Yeah, I'm carrying all those decimal places. It's good practice to do that because remember the inverse to get angle C, we did inverse sine, so it's a bunch of decimal places. So okay, that times 5 and then divided by sine of 18 was just 18 exactly. That's what we were given. So sine of 18. So 11 point, they don't give us units, just 11.56. So, and there we go.